Hello. Yesterday, Sly Sparkane put out a video challenging Dave's FE Clock Moneymaker app, and I'm not going to talk about the details of the challenge. You can go and watch that yourself. I'll put a link to it right about here. But there were a couple of things that I wanted to show in this video and to record it before it actually happened. So the challenge involves the clock app being able to predict the direction of the sun. And so he explains how he did that. Sly also built a model like this, went on Stellarium, suncalc.org, and on timeanddate.com, and all three got an azimuth heading of 286 to 287 degrees for 7:44 p.m. or 1944, May 20th. And then Sly did say he was planning to live stream the event. And so here he's got the road of an azimuth of 291. The globe sun is 286, shown here. And according to Dave's clock, the sun is supposed to have an azimuth of 318. And I think Sly was using this to calculate 308 without DST. So I ended up using the coordinates provided and located the spot in Google Earth. Then I basically used the ruler to confirm that it was 292 degrees, and depending on where you are and what the angle is, the angle could be closer to 291 point something. My channel regulars should know by now that I have written my own app that has turned into this mega project all of its own. And what I ended up doing was, since I was already working on a feature for another video, it happened to be at the right time. I was able to create not a background image, but an image overlay that goes in front of it. You can see that the branches of this tree are obscuring the text and that the path of the sun is being blocked by these trees in the background. So this part of the image is transparent. This is a still taken from Sly's video. So the first thing that I had to do was make sure that everything was lined up properly. These were the geocoordinates provided in the video. The azimuth I had taken from Google Earth. And the next thing that I needed to do was to work out the zoom level and the altitude of the camera. And so the way I accomplished that was, first I worked out the zoom level. So if you look, you can see that there are lamp posts all the way along that go all the way over to here, and then you've got another set of, I'm not sure what this is, but it goes all the way to here. And so if you measure the distance from this end to the road, it's about the same distance in the image as from here to this lamp post. So then I was able in Google Earth to eyeball this distance here and then to measure what the azimuth reading would be for roughly the same distance on this side. And I got about 282, 283 degrees azimuth. So the next thing I had to do was to change the time so that the azimuth was around 282, somewhere like that. And this distance from here to here should be about the same distance as from here to here. And so with that, I was able to get the zoom level. And if I zoom in, for example, so right now the zoom is at 10. If I zoom in, not only does the sun appear to be higher in the sky, but it also appears to be further to the left. And if I'm zoomed out all the way, for example, like this here, you can see that the sun would appear in the image for a lot longer, and then it would appear to be a little bit closer to the road than the lampposts over here, or this line. So that was how I got the zoom level of 10 to get roughly the correct zoom placement. And then the last thing that I needed to do was to get the altitude of the camera. And so if I temporarily remove the overlay, the artificial horizon computed should be right around there. And if I put the overlay back on, I've got the overlay just right around here, which is just right around where the end of this road is. So a couple of these settings I'm just guessing, and I'm doing a best effort placement, but this to me is my best effort to correctly place the sun for that time in this image. So now let's make a few predictions. Well, the first thing that you can see is that the sun should go behind this tuft of branches in this tree right around here. So that would be the first prediction that I would make, is that the sun should appear to go behind these trees right here. And at the time stated of 7:44 p.m., my prediction is that the sun should appear above this street lamp. So according to my globe earth math, that is where the sun should appear, and it should have an azimuth of 286.73. I'm also going to further predict that's about where the sun should be just before it disappears behind these trees. That should be at 8:32 p.m. The next prediction that I would make is that the sun should set at around 9:07 p.m., give or take a couple of minutes, and that it will continue to get darker and darker until we get past dusk and we get into the full of the night, which is the sun being 18 degrees below the horizon, right around there somewhere. So my prediction is that the dead of night should start at around midnight. This is probably going to be with daylight saving time, so in reality it's probably closer to 11 p.m. standard time. Longtime viewers of my channel will also know that I have added a flat earth model to my app so that I can predict where the sun or any of the objects in the sky should appear if the earth was really flat. If I use the flat earth math that I developed to determine where the sun should be on a flat earth, I've calculated the azimuth at 303 degrees, not 286 degrees. And I've also made a few other videos on this as well. But we know where the observer is and we know where the sun is. We can measure as the crow flies distance using 111 kilometers per degree rule. If flat earth really held true, that means that the zenith angle would be 208 degrees. So 0 degrees would be pointing straight up, 90 degrees would be straight ahead, 180 degrees you're looking at your feet, negative 118 degrees would actually be more bending over backwards, looking in the opposite direction. So that's more flat earth math that doesn't work. Something else that was interesting was that according to Sly, it appears as if Dave's clock says that the azimuth should be 318 degrees, not 308. That's 10 degrees difference. I got 303, Sly showed 308 minus DST. What time would it be for my math to calculate 318 degrees? Right around 9:07 p.m. So I just wanted to make this video and release it before Sly does his live stream, and we can do a compare between what a globe earth model, what a flat earth model, and see how each of those compare to what's observable reality. I made a few extra animations and made available to Sly, so you might end up seeing some of this on his channel. And I'll just leave it like that for now, and we'll see how this matches his observations on the 20th. With that, that's going to be it for now. Thank you for watching, and I'm going to see you in another video soon enough. So bye for now.